So, this is the 12th, and I'm happy to say the last in a series of video-based lessons that will describe relatively briefly the process of normalization of relational tables with redundant data causing modification anomalies. In this video, we define the concept of database normalization designed to mitigate modification anomalies caused by the presence of redundant data in a relational table. The concept of the concept of functional dependencies between columns in a relational table is the key to understanding data redundancy. And by eliminating different types of functional dependencies, the table conforms with an increasingly higher and better normal forms. At the end, we describe a relatively simple synthesis procedure that will guarantee a high enough normal form for our databases to practically eliminate any possibility of modification anomalies. This material is covered in the first part of Chapter 7. We begin by placing database normalization in the context of DB development, right after the conversion of ERD into relational tables, but before moving to the physical design stage, which is, which would be sort of a natural next topic of the class. Should we have enough more time, which we don't. Normalization is typically the last stage of logical design and is defined as a systematic process of removing redundancies from relational tables. As we already mentioned in the outline, these redundancies create table modification anomalies, have unpredictable effects, and make tables difficult to use. Normalization process is used to identify different types of functional dependencies, or FDs, causing the redundancies, and use several normal forms to eliminate them. But before we get into FDs and normal forms, let's show the different types of modification anomalies resulting from poor table design. Let's take a look at two different designs of a simple sales database. Design number one, in the top part of the slide, shows salespeople from salesperson table generating quotes in the quotes table for items from item table with quantities shown in quote detail table. Design 2 shows a single sales table with all that information. Which of the two designs is worse and why? You can kind of sense that design number 2 is bad, or certainly not good. Redundant data on salespeople, quotes, and items are everywhere, even for such a small example. You can only imagine the redundancies with a more realistic scenario. When you modify design number 2 sales table, so the one from the bottom of the previous slide, you will run into all sorts of problems caused by the redundant data. These problems, called modification anomalies, generally fall into these three categories at the bottom of the current slide. Number 1, insertion anomalies. Number 2, update anomalies, and number 3, deletion anomalies, described on the following slide. Okay, insertion anomaly occurs when extra data beyond what we want to add must be added to the database. If we wanted to add another product, okay, let's go back here. If we wanted to add another product, product with item ID 4444, okay, and the price $50, we would also have to add a quote for that product, because that's what the quote ID over here and item ID would sort of mandate, because they are a compound primary key, and no part of the primary key can be null. So going back here, update anomaly occurs when it is necessary to change multiple rows to modify attributes of a single entity. To change the rank for Gina from junior to senior, Gina, junior to senior, right here, 2 rows would have to be updated instead of just 1 in salesperson table right here. Okay. Finally, deletion anomaly occurs when deleting 1 row causes unintended loss of data. This would be the case if we delete either first or last row in the design number 2 over here. Okay, the info on item 111, certainly on item 222, and their prices would be lost. Okay. So the question is, how do we systematically how do we systematically, wrong direction, deal with these anomalies? The answer is the process of normalization, okay, which will remove data redundancies and prevent modification anomalies. In order to understand normalization, however, we first need to discuss the concept of functional dependencies, or FDs for short. An FD, described in the middle of the slide, okay, is a constraint on two or more columns in a relational table. One column, X, on the left-hand side, LHS, of an FD determines or is a determinant of another column Y if there is at most one value of Y for every value of X, just like a math function. Think of it that way. All right, so this X arrow Y thing. Okay, different X's can have the same Y, but not the other way around. In other words, one, the same Y cannot be associated with different X's, because then that's not a functional relationship. Okay, for example, person ID is functionally defines functionally the salesperson name, or salesperson name is functionally dependent or determined by the person ID. So the person ID determines or is the determinant of SP name. It's all a mouthful, but it's very simple. Since there is at most one name associated with a salesperson ID, which is ultimately the definition of the primary key. So there are two ways to summarize functional dependencies, or sort of capture them. Number one is the list, like the top of the slide, and number two is the diagram at the bottom of the slide. Okay, this diagram shows both of them, both ways for the design number two, the bad design, right? This one over here, for the sales table. Okay, we will label each of the functional dependencies with an index, FD1, FD2, FD3, and FD4, so it's easier to sort of refer to them later. For a more complex such situation, FD lists, this is preferred to the FD diagrams, because these diagrams can quickly become difficult to read and interpret. Okay, so how do we go about identifying all the FDs for a table? Okay, as the previous slide shows, the statement about uniqueness used to identify primary keys are the easiest. This is how we came up with all four of these FDs over here. Okay, using the primary key sort of definition. Okay, uniqueness. So those derived from 1 to M or 1 to many relationships are a little trickier to identify, and they're always derived from child to parent table, not the other way around. Salesperson quote relationship, okay, is one such example. If we know the quote ID, we know everything about the salesperson that provided the quote. And since there can be only one of those, and this is the definition of functional dependency. This means we need to modify our FD2, okay, where quote ID determines quote date, or in other words, quote date is determined on quote ID. So it's not going to include only that, but it's going to include all the salesperson information as well. And this comes directly from this design to table, right? If I know quote ID, I know everything about Joe, his ID, his first, last name, and rank. Okay, so that is then added here in the middle of the slide, right? Quote ID determines not just the quote date, but person ID, name, rank, and anything else associated, right? Then that in turn, now FD2, as shown here, okay, contains the so-called transitive dependencies. Since quote ID determines person ID, and since, according to functional dependency number 1 from the previous slide, right there, the person ID determines salesperson name and rank, then the quote ID, okay, transitively determines salesperson name and rank as well. This is shown here, in the abstract. Okay, so you can definitely detect redundancies in this sentence, by looking at these transitive dependencies. Okay, so this might be a good place to pause this presentation.